Welcome back to Business Mathematics 1. I'm Eric from Mathematics Study Program, Faculty of Mathematics and Natural Sciences, ITB. So for today, we are still going to discuss additional application of derivative. So the main focus that we are going to talk or discuss is about the absolute extrema in the interval that is not closed or bounded, and the application on the marginal analysis. Let's start. Okay, this one is we usually call the general optimization problem. We have learned of this, and what about on the interval that is not closed or bounded? So when the interval is not closed or bounded, and if f is a continuous function that has an absolute extrema, then that has absolute extrema, not only, okay, yeah? Then it will occur at a relative extremum or endpoint contained in the interval. But in this one, we have to know the monotonicity to confirm that it is the relative, that is the absolute extrema. Okay, yeah. So this one, we have maybe at this interval, in this interval until infinity, I have the absolute maximum happen at the endpoint. What about this? This is absolute minimum happen at the endpoint too. What about this? This is the absolute minimum happen at the stationary point, and this one absolute minimum maximum happen at the stationary point. Now here you have to find the relative extrema again and confirm that the critical point, don't forget what is the critical points, it is either singular point or stationary point, are the absolute extrema. Let's look at the example on marginal analysis. A manufacturer estimated that when key thousand units of a particular commodity are produced each month, the total cost will be given by this in $1,000, and all units can be sold at a unit price this dollars per unit. Determine the level of production that result in maximum profit, and what is the maximum profit. Don't forget, how do I find the profit? This is the difference between the revenue and the cost. We usually have the profit is revenue minus the total cost, and we have to find the maximum profit. The second one, at what level of production, we mean that at what quantity is the average cost per unit, AQ, that is CQ divided by Q. This is the average cost. This is the total cost of producing Q unit divided by Q unit produced. So this is the average cost per unit. So how at what level Q is the average cost AQ is minimized. And what about, and at what level of production is the average cost per unit equal to the marginal cost, that is C prime is Q. Okay, let's look. The profit function is given by this one. This is the unit price times the quantity produced. So this is the revenue minus the cost. We can substitute the revenue here, and we can simplify this into this. Don't forget the units in $1,000. So we will find the maximum of profit PQ at interval key could be greater or equal to 0 and less than infinity. Why? Because key is a quantity, is a demand. So it should be positive. It should be positive. It should be non-negative. Okay, it can be 0. Okay, but it is a trivial case. Okay, so the global maximum can happen at the first one is stationary point. So we have to find P prime Q, and this is P prime Q, and the stationary is given by Q equals 6, the stationary point. Here you have to find the sign of diagram of P prime. Why? Because we are dealing with the not bounded interval. Okay, so we have this one. Don't forget the quantity starts at 0. So you have like 0 to 6, 6 to infinity. Okay, so the profit function is increasing on this and decreasing at 6 comma infinity. So all the way it will go up and down. So 6 is gonna be the maximum of the profit. with local maximum q equals 6. There are no singular points. Don't forget, this is just a polynomial. And the point is given by q equals 0. And so it can be checked that P6 is this and P0 is minus 40. So the maximum profit happen at level production key equals 6,000 units with maximum profit 17 and $600. Of course, you can determine whether this is maximum minimum using the second derivative also. Okay, yeah. Let's talk about the second one. How do I want to find Q such that the average cost is maximized? So I want to find the stationary point of this. And AQ f prime Q, the derivative of AQ with respect to Q is the derivative of CQ divided by Q. And CQ is given by this, Q is this. I want to find the derivative. Don't forget this is the function of Q divided by the function of Q. So you have U divided by phi. And how do I find the derivative? U prime phi minus U phi prime divided by phi squared. So I can simplify this into this, and I can factor out 0.4. So I have this. You can factorize q squared minus 100, and you have this. And you want to have the sign diagram. So the sign diagram is given by this. You can check for all these points here. So it is go up, down, down, up. So the minimum happen at x equals 10. Okay, yeah? The average cost has local maximum at q equals minus 10 and local minimum at q equals 10. And it can be proved that q equals 10 is the global maximum from 0 to infinity. Why? Because from 0 it is increasing, but decreasing until the infinity. So it should be the local, the global, the absolute maximum. Okay, there are no endpoints. Okay, and there are no singular points, but there is q here. Yeah, but q equals 0 is not on the interval. Okay, yeah, q is cannot be 0 because this is division by 0. So the critical point is q equals 10, and the average cost is minimized at level of production 10,000 unit. That's the stationary point of AQ. Okay, yeah. Last one, we look at when I want to find Q such that the average cost equals the marginal cost. So I can just plug in here. Okay, yeah, and this is this, and you can get to the right hand side and you have this one. So when Q equals 10 and Q equals minus 10, the level of production is the same as the marginal cost. Okay, yeah, and the average cost per unit equal to the marginal cost. C prime Q when the level of production is 10. Don't forget the units is in 1,000 units. Then B and C answers are all the same. Okay, yeah, because this one. If we want to find the minimum of average cost function, it can only happen at the stationary point. Okay, yeah? And to find the stationary point, I have to set the derivative which is equal to 0. Find this one, and you have this one. What is this? It means that this one. So when the average cost minimized, when the marginal cost equals the average cost. Okay, yeah? This is the first rule for the marginal analysis. The average cost function is minimized when the average cost is the same as the marginal cost. Second one, if we have the profit function given by RQ, the revenue minus the cost, and we want to find the maximum of this, we can find the stationary point. So I want to find Q such that P prime Q equals 0. But to have this as the maximum, I have to clarify that that P double prime Q is less than 0. This is the second derivative test. What is the P double prime Q? This is R double prime Q minus C double prime Q. Okay, it means if we want to maximum the profit, it will happen when R prime key equals C prime key from this, and R double prime Q is less than C double prime Q from this. Okay, so we have already finished talking about the absolute extrema when the interval is not bounded or closed, and we have already discussed about the example that is on the marginal analysis. In the later video, we will learn on the other example of the additional application on the derivative. Thank you.